Hi folks, welcome to this lesson on angle formulas. So the big question we're going to investigate is essentially this. Does sine A plus B equal sine A plus sine B? Like, can you just split them apart like that and have it work? We could try some numbers in our calculator and see what happens. You can use your lucky numbers. I'm going to use 3 and 7. So first of all, I'm going to find the sine of 3 plus 7. I could have just written sine 10. That would have been better. And I can write sine 3 plus sine 7. And we can see that they give us different values. They're not equal. And it brings up kind of a deep thought in mathematics that although proving an identity is a high bar, disproving one is really easy. All you need is one counterexample. So it's true, if you happen to have the lucky numbers of 0 and pi, this will work. But for most numbers, you won't get this property to work out. The short answer is that no, they don't work out. So then it begs the question, well, what does sine of A plus B equal? And usually I do a proof that is fairly lengthy here, but I can kind of already feel the eyes glazing over. So instead, I'm going to link in the video description a proof of why these formulas work. Instead, I'll give you them. But if you're not satisfied with just being given the formulas, that makes me really happy. And then you can just check out that link in the video description. So if you watch the proof, or if you just want to take my word for it, here's the result. Sine A plus B turns out to equal sine A times cos B plus cos A times sine B. I like to keep them in alphabetical order. Different people like to do them different ways. So for any two angles that you're trying to add together, that's a way of finding the sine of those two angles added together. A sort of thing that jumps out from that is that we get also a double angle formula. If you had sine A plus A, so two angles added together, that would be the same as the sine of 2 times A. That would be sine A cos A plus cos A sine A. They'd all be the same, or in other words, 2 sine A cos A. These are ways that we can rewrite some trigonometric functions either as the sine of a double angle or as splitting apart with a smaller angle. Cosine of A plus B turns out to equal cos of A times cos of B minus sine of A sine of B. And that means that there's also this sort of double angle version. What if you had the same angle twice? Well, that would be cos of 2A, and that would equal cos A minus sine A sine A. Okay? Or, better yet, you could write that just as cos squared A minus sine squared A. Okay? That's an expression for the cosine of double an angle. Now, because of Pythagorean identities, there are actually other ways that you can write that. So we know that the Pythagorean identity like this exists. Sine squared plus cos squared equals 1. So we know that sine squared is equal to 1 minus cos squared theta. And also you could rearrange that to say cos squared is equal to 1 minus sine squared theta. So you can do a couple of substitutions here. This is sort of the base version of the cosine double angle formula. But if you made that substitution with the cosine that says 1 minus sine squared, you could say 1 minus sine squared goes in for cosine squared. 1 minus sine squared A minus sine squared A. Or 1 minus 2 sine squared A. This is another way of writing the cosine of 2A. Okay, so there's this version here. There's this version. Or there's even a version where you make a substitution instead for sine squared, which is equal to 1 minus cos squared. So I'll just make that substitution in here. Cos 2A is going to be cos squared A minus sine squared, which is equal to this thing here, 1 minus cos squared A. Or if you put that all together, you get 2 cos squared A minus 1. So 3 different versions of the cosine double angle identity. And rather than prove that these work, why don't we just see if they work? So the one that I looked at before was the sine of 3 plus 7, or sine of 10. And we can check in our calculator. Is it really going to be equal to the sine of 3 times the cosine of 7? So A would be 3, B would be 7, plus the cosine of 3 times the sine of 7. Let's see if it works, at least for these numbers. So sine of 3 plus 7, or sine of 10. Let's see, sine of 10 is just that. Okay, now let's write it the other way around. It was going to be sine 3 cos 7 plus cos 3 sine 7. It happens to work. Okay, and again, the proof is in the Khan Academy video. Seems like a lot to keep straight, right? But we do have this handy-dandy formula sheet, and now we've kind of got all the things explained that go on there. So if you've got two angles added together and you're looking for the sine, well, here's the formula. Two angles subtracted and you're looking for the sine, there's the formula. Same for cosine and tangent. If you've got a double angle, that just comes from both of them kind of being a. So sine 2a is equal to this. Cos 2a has 3 different versions. And tan 2a also has an identity. So we'll work on playing with these, and today it will really just be playing with these angle identities and seeing what they can do for us. And then tomorrow we'll probably do some proofs. So we'll start with this really contrived situation where you've got just an ugly expression here, and we're wondering, is there an easier way to write it? So I've got cos 17, cos 43, minus sine 17, sine 43. I've got the same angle happening twice. What I really want to find in the formula sheet is where that form is, where it says cos cos minus sine sine. Let's head up here. Cos cos minus sine sine. Oh, I'm looking for... Hey! Here it is. And it's equivalent to just cos of those two angles added together. Okay. So from that, we can say, oh, I could just rewrite this as cos of 17 plus 43 degrees, or the cosine of 60 degrees. And the cosine of 60 degrees is 1/2. Maybe I'll take a second here and just refresh our memory on the trig values. I know that YouTube is very litigious about its copyright stuff, so I won't sing it, but I am thinking about the Jackson 5 tune, ABC. So I've got these points, they're easy to find. This is 0 degrees, 30 degrees, 45 degrees, 60 degrees. That's pi over 6, pi over 4, pi over 3, pi over 2. Okay, and I've got all these points are over 2. And the x's are cosine, the y's are sine. And it's as easy as 1, root 2, root 3. For sine, same thing. 1, root 2, root 3. I'm going to put the tan values in red, which would be 0, 1 over root 3, which you can also write as root 3 over 3, 1, root 3, and undefined. So tan in red. Okay. I also know this stuff. ASTC, and again, cosinus x. So that's how I know that the cosine of 60 is 1/2. If I looked at the original form that I was given here, cos 17, cos 43 minus sine 17, sine 43, I never in a million years would be able to evaluate that without a calculator. But once I put it into this nicer form, then I can figure it out. It's just asking cos 60, and we know that's 1/2. So let's try another one in radians. The form that we're seeing here is sine cos plus cos sine. Let's see if we can find that. Sine cos plus cos sine. Sine cos plus cos sine. Oh my gosh, that's a sine addition identity. So this thing can be written as sine of 2 pi over 5 plus pi over 10. It's as if this is our A and this is our B. A and B. Okay, so when we go to add them together, we just need to add those two angles. Now, if you want, you can work in degrees here. I'm thinking of this as common denominators, so this would be 4 pi over 10. Oh my gosh, so that would be the sine of 5 pi over 10, or the sine of pi over 2. And the sine of pi over 2, we know from our unit quarter circle, is 1. Okay, it's the y value at 90 degrees, or pi over 2. The last one, it takes the form 2 sine pi over 12, cos pi over 12. So it's as if this is our theta, or our a. Let's see if we can find that kind of form. 2 sine cos. Maybe pause, take a look for it. I'm noticing it right here. Okay, so it becomes 2 sine, or sine of 2a rather. So I'm just going to write that down below. This is the identity that it reminds me of. Sine 2a equals 2 sine a cos a. Okay. So for me, like, the a is the pi over 12. And this whole thing, just like this, is equivalent to this kind of form. It's equivalent to just writing a sine and doubling the angle. Okay, but for us, that angle is not just a, is pi over 12. And the double of pi over 12 would be 2 pi over 12, or 1 pi over 6. And sine pi over 6, we can find that on the unit quarter circle. It's just a half. Now you can verify that it's equal. I'm going to go to the calculator and do that. So I've written 2 sine pi over 12 cos pi over 12. It gives me 0.5. I'm in radian mode here. But by rewriting it in this form, we could find it analytically. Okay, so we're looking for opportunities to use these formulas. One thing that does for us is allow us to expand our definition of the trig ratios that we know exact values for. So up to now, it's only been multiples of 30 degrees and 45 degrees. But we can now find exactly what sine 75 is, because we can think of sine 75 as the sum of two angles we know about. It's the sum of our lucky angle of 30 and our lucky angle of 45. Okay. Now that is not equal, to be clear, not equal to sine 30 plus sine 45. We've got these formulas. They tell us what is okay. So let's go check that sine addition formula again. Sine addition is right up here. Okay. And it's sine cos plus cos sine. So it'll be sine of 30 cos of 45 plus the cos of 30 times the sine of 45. And we actually know all those values. The sine of 30 is a half from the unit quarter circle. The cosine of 45 is root 2 over 2. The cosine of 30 is root 3 over 2. And the sine of 45 is root 2 over 2. So what does this give us? It gives us root 2 over 4 plus root 6 over 4. Or just root 2 plus root 6. Mercifully, I already had a common denominator. There's the exact value of sine 75. If you have a really fancy calculator, it might tell you that. I don't know if mine will. Let's see, sine 75, it will only give me the decimal approximation. So our value is better. It's exact. I think we're going to feel more comfortable working in degree measure. So if I saw one of these, cos of negative pi over 12, I could work entirely in radians, but I might also think, hold on, I know pi over 6 is 30 degrees. Pi over 12 is going to be half of that. It's going to be 15 degrees. So this question is really asking me, what is the cosine of negative 15 degrees? And I might ask, how can I build negative 15 degrees using numbers that I know about, multiples of 30 and 45? One way, though not the only way you could do it, is to say it's the cosine of 30 minus 45 degrees. Okay. Once you have it written like that, you can probably find the exact value. So we head and look for that cosine difference formula. Cos of A minus B is right here. It's cos cos plus sine sine. Okay, so cosine of 30, cosine of 45 plus sine of 30, sine of 45. And again, we can just work these through. Cosine of 30 is root 3 over 2. This is root 2 over 2. This is going to be 1/2. And this is going to be root 2 over 2. And that's going to give us root 6 over 4 plus root 2 over 4. Oh my gosh, it's going to give us the same answer because the order of addition doesn't matter. But it does actually make sense that it's a big positive value because at negative 15 degrees, you're right here on the unit circle. Your x value is going to be a big positive number. It's going to be close to 1. Now somebody might say, oh, well, couldn't we do it differently? Couldn't we have said that this comes from the cosine of 45 minus 60? If you do that, then you'd go cos 45, cos 60, plus sine 45, sine 60, and I guarantee you, you'd get the same numbers. Here, we can do it in quick time. Ta-da! Same result. If you feel like you're getting the hang of this, feel free to just pause it and try C on your own. Okay, so I'm looking at 105 and thinking, how can I compose it out of angles I know about? Well, 105 is 60 plus 45. And I'll tell you a quick little trick is that if it ends in a 5, and it's not already a multiple of 45, you're probably going to need to use 45. So it'll be 45 plus whatever's left over. Okay. Now I need to head to my formula sheet. Tan addition is right here. It's tan A plus tan B over 1 minus tan A tan B. So that would be tan of 60 plus tan of 45 all over 1 minus tan 60 tan 45. And we can work this through. Tan of 60 is root 3. Tan of 45 is 1. All over 1 minus tan of 60, which we already said is root 3, and tan of 45, which is 1. So we get root 3 plus 1 all over 1 minus root 3. I am 100% fine with you leaving your answer in that form. But if you think back to your 521b stuff, we didn't really like radicals in the denominator. And the way that we got rid of them was something that we've been doing a bit anyways, is by using conjugates. Okay. And so what would we get if we multiplied this out? We would get, on top, we'd get 2 root 3, okay, plus 1. So the root 3's are coming from this and from this. The 1's are coming from this. And then root 3 times root 3 would give us a 3. So if I just FOIL out the top, that's what I'm going to get. On the bottom, I would get 1 plus root 3 minus root 3, because they're conjugates, minus 3. So I might get something like this. 2 root 3 plus 4 all over negative 2. Okay. And you could say, I hate having negatives in the bottom, so you could times both top and bottom by negative 1. That would give us negative 2 root 3 minus 4 all over 2. That's pretty nice as well. You could factor the top, take out that 2, and you'd have negative root 3 minus 2 all over 2. These would divide out. All this stuff in red is simplification that kind of comes from 521b stuff. The main thing of plugging into the formula gets us to what's in blue over here. So this is okay in this form. But you'll probably see, if you throw it into a fancy calculator, that it'll come out to this answer of negative root 3 minus 2. I'll walk you through one last one, the sine of 195. So again, I mentioned that if they end in a 5, they probably need a 45 and whatever's left over. And this can be annoying because 150 is not on the unit quarter circle. So first off, we'll take a look at the formula sheet. Sine addition is the very first one that you see, sine cos plus cosine. So that'll be sine of 45 cos of 150 plus cos of 45 sine of 150 degrees. And for sine of 45, we know that's root 2 over 2. Cosine of 150, just remember, it's going to be the same as the cosine of 30, because it has a reference angle of 30, which would be root 3 over 2 from a quarter circle. But cosine's negative in this quadrant, so you're going to have that negative angle. And all the other ones we've done so far have only used angles from the first quadrant, to sum up to whatever. Cosine of 45 is root 2 over 2. Sine of 150, again, it's going to have that reference angle of 30. So this is stuff we did in Chapter 4, finding sine and cosine of any angle on the first rotation. So it's going to have the same sine as 30 degrees would. It's also still going to be positive in this quadrant, so it'll stay positive. And then when we work this thing through, well, let's see what we get. We're going to have negative root 6 over 4 plus root 2 over, not over 2, over 4. Or you might see it written this way, root 2 minus root 6 all over 4. And if you're ever not sure, you can check in the calculator. See if that exact value is the same as the decimal approximation we get. So sine 195 as a decimal is this. That thing that I just got was root 2 minus root 6 all over 4. If they give me the same decimal value, they're equivalent. However, this thing that we've got over here is exact, so we get to feel smug and superior to our calculator. All right, the last thing we're going to do today is write some functions as a single function. And I think what we really want to do is look for opportunities to exploit some of these formulas. So I see here 10 sine x cos x. I want to go to that formula sheet and see what that reminds me of. When I look at this, it reminds me the most of the double angle formula for sine. It's a sine times a cos. There's not a 2 in front of it. There's a 10. That's annoying. But there are no other terms like there are in some of these. So I'm going to make that association and hope that it helps me. In my mind, I'm thinking this. Sine of 2a is equal to 2 sine a cos a. Unfortunately, I've got a 10 here. Let's see if I can build essentially this kind of statement, though. So if I factored out a 5, I could see it written like this. This is equivalent to what we just had. Okay, I just wrote it like this, but I was trying to see this kind of expression. And from the identity, anytime you have 2 sine of an angle times cos of that same angle, you can rewrite it in this form. Okay, and we proved why that's true when you add the same angle twice. If you want a deeper proof, head to Khan Academy video that's linked below. So that means that, maybe I'll color code this. This whole bit here can be rewritten as sine of 2x. What's going to happen to that 5? Well, it's just going to stay. So in the end, this is 5 sine of 2x. And that's a simpler function for us to think about. So it turns out you can play with a lot of trig functions and turn them into more convenient forms, which will be important for integration, but it's also important for a lot of digital signal processing. Here comes our last one. We've got cos 2x plus sine squared all over cos x. So when I see that cos 2x, I pretty much know I'm going to have to use a cosine double angle identity. And here were the three forms of them. Cos squared minus sine squared. 2 cos squared a minus 1. And 1 minus 2 sine squared a. You can use any of those substitutions and hopefully get it down to a simpler form. That said, some may be easier than others. So I'll run you through at least two ways of doing this. If I chose to substitute using this one right here, let's see what happens. I would have, instead of cos 2x, I would write cos squared of x minus sine squared of x. Okay. The rest would be as is, plus the sine squared x that was already there over the cos of x. And you can see the sine squareds are going to divide out, and I'll have cos squared x all over cos x. And one of those cos x's will divide out for a final result of cos x. That was pretty slick. I guess partially because we got lucky and we chose a really simple way to approach this. Okay. What if instead you had chosen a different one? What if you had chosen to replace cos 2x with, say, this one here? Well, let's see what would happen. So 2 cos squared x minus 1 is the substitution we'll make. Everything else will stay the same, so I'll keep that in black. Plus sine squared x over cos x. And from here, it looks a little messier. Now, it's not impossible to deal with. Let's see what would happen. What if I split up that 2 cos squared x as cos squared x plus another cos squared x minus 1 plus sine squared x. And this is all over cos x. It turns out that if you took, say, one of these cos squareds plus one of these sine squareds, what would they make together? They'd make 1. So you'd end up with cos squared x plus 1 minus 1 on the top all over cos x. Or in the end, cos squared x over cos x or cos x. There are a bunch of different paths you can take to end up at the same place. Some require a little more insight. Some are more elegant than others. We probably did the most elegant way first. You could also have substituted with 1 minus 2 sine squared a, and that one might have been a little less painful than the one we just did, but a little more painful than the first one. In terms of practice, you can head to page 306 and take a look at numbers 1, 2, 4 ADE, 5, and 8 ABC. I hope this has been helpful. Good luck with the material, folks, and take care.